This is lecture 12, the single facility location models, and for IE 4355 facilities planning. And the lecture material for this video is discussed in chapter 10 of the textbook for this class, single facility location models, chapter 10. As always, we start our lecture with the objectives for this class. We've been talking about this lecture, these objectives since the beginning of the semester. And for this particular lecture, we're focusing on the first objective, which is to develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. So the agenda for today, we are going to do a brief introduction on location models, and we're going to discuss what is the idea in terms of these models, how they can be implemented, and what is the purpose of having these type of models for a practical point of view. For example, if you were to expand the location of warehouses in your company or the company that you end up working with, identifying the place to go in terms of expanding that network. So for example, in this I-35 corridor, you have seen a lot of warehouses for Amazon. And so that type of planning takes the use of these models, understanding the demand, understanding the coverage, and then making decisions on where would be the best place to locate the next facility. So the learning objectives for this lecture is to learn and analyze facility location models. So let's look at the introduction. There are types of models include the single facility location model, the location model, and the quadratic assignment model. So for facility location problems. So in this lecture, we're going to focus on the single facility location model, which idea again is to select the location for the next facility for expansion. So the single facility location model, for this, we have two types of objectives that are typically used from a practical point of view. The first one is the minimum location problem, which looks at minimizing the sum of the weighted distances between the new facility and other existing facilities. And we have the minimax location problem with minimizing the maximum distance between the new facility and any existing facility. So when we talk about distances, most of the time we are referring to rectilinear distances, which are represented in this figure. We take into account the x-axis and y-axis in estimating these distances. So distances, again, we look at the y and the x-axis in this figure. We have the points that are yellow are representing existing facilities, and those that are red represent the new facility. And we want to estimate the distance between this new facility and the existing facility. And we do that by using the rectilinear distances. So we know y and x. Actually, we don't know y and x for this new facility, but we want to know, we want to estimate once we have a possible location, what will be the distance from this point to the other location or the other facilities. So in terms of the y direction, we have the absolute value between y and minus bi. Bi is representing the distance from the origin of the location of facility I. And so we do the difference, y minus vi, and that tell us what is the distance in that direction. Same thing for X. So we have AI. AI is representing that distance from the origin. So AI is the distance from the origin. So let's call it this 0, 0, right? So we are measuring that distance. Same thing here, BI for the y-axis. And we want to estimate the distance from this new location to those existing facilities. We don't know that yet. We don't know where that location is going to be. So that's why we have y equals this question mark and x equals question mark. But when we are searching for that best location, we need to have options to pick up or to select from. So using those options, we are going to, so for every option, we are going to estimate the distances from the options to each one of the existing facilities. So the existing facilities are those in yellow. Okay. So in this case, we are trying to estimate the distance from this possible location and this existing facility. So if you look at the y-axis, that distance is the absolute value between, or the absolute value of the difference between y and bi. So y is going to be that possible y coordinate or y distance. So in this case, that will be this distance. And bi is this distance from the origin to, in terms of y, to that location. If we look at the x-axis, is the same thing. We are looking at the this additional distance. So this will be the distance to the new location. That will be x. And then the distance from the existing location will be all this. So the difference in terms of distance will be the absolute value between x minus ai. So the total distance is what we have here at the top, is the summation of the absolute value of x minus ai plus the absolute value of the difference y minus bi. W is equal to the number of trips from this existing location to the new location. So that's basically a weight that we assign. So WI is representing that weight. So if we have a lot of trips going from the existing location to the new location, then that facility will have a highest weight when compared to a facility in which you don't have that many trips to. So you want to make sure that the new location is close to that those facilities that are required to interact the most with that new facility. So in order to consider that, we multiply that weight 2 times the distances for x and y. So this is what we call the weighted distance. So the minimum location problem with rectilinear distances can be formulated as follows. We have the minimization of, or the objective function is the minimization of this function for x and y. So we want to minimize the summation from I to m. M is the total number of existing facilities, and you go one by one. For each one of the facilities, you want to compute this equation, which is the weighted distance. And then you're going to sum the whole thing based on that possible location of the new facility. Okay, so x and y, those are unknowns. So we want to find the best location in terms of x and y that will minimize the summation of this weighted distance. But if you look at this equation, if you look at this objective function, this whole thing, you can separate them in 2 pieces, which is what we are doing here. So this equation can be separated in 2 pieces. We have the weighted in terms, the weighted distance in terms of x and the weighted distance in terms of y. So we can separate them into 2 separate models. One that is focusing on the weighted distance of x, one that is focusing on the weighted distance of Y. So how can we use that information that I just discussed? Let's look at this example. In this example, we have facilities 1, 2, 3, and 4 are located at points 8, 5, 4, 2, 11, 8, and 13 and 2, respectively. So these are the locations of the facilities. These are existing facilities, and they are located on those coordinates. It is estimated that there will be 9, 6, 4, and 12 trips per week, respectively, between facilities and a proposed new facility. Find the location of the new facility. So we have the location of the existing facilities, plus we have additional information. So we have trips, 9 trips. We have 6 trips between this facility and the proposed new facility. And we have 4 trips between this facility and the proposed new facility. And we have 12 trips between this existing facility and the proposed new facility. So the question is, if we were to locate this new facility, where would you place it? Close to which of these facilities, and so on. So we can solve this problem by using this information. We want to minimize the weighted distance. So the minimum problem, location problem with rectilinear distances. So if we look at the coordinates for each one of the facilities, we have a list for the X and the Y's, and we also have the trips, right? So that's the information we need to formulate this objective function. So if we substitute that information into this equation, then we obtain this equation. And as you can see, the unknowns are X and Y. X and Y are the coordinates for the new facility. So whatever X and Y is where you're going to be placing that new facility in this space. Okay, so we want to make sure that whatever will or that optimal solution, that location, is going to be minimizing this function. So let's reformulate as an LP model or as a linear programming model. We have the minimization, which is the objective function. And then using this substitution, in which we let the absolute value of X minus AI be equal to Ri plus Si. And this is going to be X minus AI is going to be equal to Ri minus Si, in which Ri and Si are going to be always greater or equal to 0. So using that information, then you can substitute this into the model. So as you can see now, this is now represented in terms of Ri, R1, and S1. Okay, so this piece right here, which is the piece for X. Okay, so that part of the function is now substituted in terms of Ri and plus Si. Okay, and our constraints for this model are going to be X minus this piece, X minus this piece, and that has to be equal to 4, to 8 to 4. X minus this piece has to be equal to 11, and this piece has to be equal to 13, which are the number of trips for each one of these pieces of the equation. I'm sorry, those are not the weight, those are the current X coordinates of the existing facilities. Okay, so this piece of the equation has to be equal to that piece of the equation. Okay, so essentially what we are doing is solving for the unknowns. Okay, so we let this equal to this, and then we are solving for A. So A is the right side of this equation, and then you move the rest of the equation to the other side. Okay, so those are the constraints that we have here. And we know that Ri and Si has to be greater or equal to 0. And we are doing all this because we have to deal with this absolute value. Okay, so that's the way we basically take that absolute value out of the equation. So we make this piece a positive number. So we make sure that this side of the equation is always positive. And then by solving to AI, we have set up these constraints. Okay, so now we do the same thing for the Y axis. So now we are looking at this piece of the objective function, and we proceed in the same way. So we can solve this problem using any solver. If you're familiar with linear programming, if you have taken that class, IE 3340, you know that linear programming models can be solved in Excel, AMPL, Cplex. We have discussed those software or LP solvers as part of the class. But this will be the linear problem in the X direction, and this will be the linear problem in the Y direction. And if we solve this to an optimal solution, this is the value of the objective function, 93, and the coordinate for the new facility in terms of X would be equal to 11. For the Y, the objective function will be 51, and the coordinate for Y will be 2. So 11 and 2, and the cost will be 144. Okay, but if you don't have access to a solver, we can also solve this problem using an algorithm. So this will be the optimal location of the new facility. This point right here with Y equals 2 and X equals 11. Based on the solution that was provided by the software. But we can obtain the same solution, and you will see this algorithm is going to provide us with the same solution. This is called the cumulative weighted or the cumulative weight algorithm. So the idea, again, we set up the parameters for each one of the facilities. We have the location of the existing facilities in terms of A and B, and we also have the weight for each one of the facilities. And we are going to use these two parameters, the weight and the existing X coordinates for the existing facilities, to find the location in terms of X for the new facility. And we are going to use this, the location of the existing facilities in terms of Y, and the weight for those facilities to find the location of the new facility in terms of Y. So what are the rules? The rules to determine the optimal value of X. We are going to arrange the AI's values in increasing order. We're going to compute the sum of weights, in this case, the trips for each value. And the optimal X is the value at which the cumulative weight is greater or equal to half the sum of the weights. The rules to determine the optimal value of Y: we arrange the V values in increasing order. We compute the sum of the weights or the trips for each value. And the optimal Y is the value at which the cumulative weight is greater or equal to 1/2 the sum of the weights. So let's look at this table, which is again the information that I just showed you. So we have 4 facilities. We have the coordinates in terms of X for those existing facilities. We have the coordinates in terms of I'm sorry. This is the calculation of X star. So this is the calculation of the new facilities coordinate in terms of X. So we have the information for the existing facilities for in terms of X. So we have the facility name 2134 in increasing order. So going back here, arrange the AIs in increasing order. Okay, so AIs are here. You can see they are arranged in increasing order. So that changes the order of the facilities because they're arranged based on AIs. And then we have the information for the WIs, and we are doing the summation, cumulative summation for those AIs. So 6 plus 9 is equal to 15. 15 plus 4 is equal to 19. And 19 plus 12 is equal to 31. So these are the sum of the WIs. We compute the 1/2 summation of WIs. So that will be 31 divided by 2, and that's 15.5. So in this, so going back here, the optimal X is the value at which the cumulative weight is greater or equal to 1/2 of the sum of the weights. Okay, so in this case, that would be value 19. Which is going to give you a coordinate for X, which is going to be equal to 11. So X star is going to be equal to 11. Calculation of the optimal Y star, same process. We ordinate, we arrange them in terms of PIs. We do the sum of the weights. And then we compute this value, which is again 15.5. So if we look at the sum of the weights, the one that is greater or equal to this number, 1/2 the W's, the summation of the W's is this number, 18. So what that means is that the location of facility in terms of Y is going to be equal to 2. Okay. So the optimal location is 11 and 2. As we found here, if you compare our solution, it's the same, 11 and 2. So this algorithm provides you with the optimal solution of the problem without having to use a computer program. So as we did for the computer software, this is going to be the same solution, 11 and 2. And the objective function value is equal to 144. Okay, so that concludes this lecture on the single facility location model. And we discussed this problem, and we also discussed the practical applications, like again, for expanding network of warehouses or network stores, supermarkets, any type of industry that requires logistics, like UPS, Amazon, eBay, Dell. They use these type of models frequently, and it helps them planning for longer term and expansion. So that's all. Thank you.